Every object has a natural frequency. So when you match that natural frequency, you can increase that object's amplitude. For example, if my kids are swinging on the swings and they're going back and forth with some regular frequency, like pendulums do, if I decide to push and I get my pushes to match the frequency, the amplitude of their swinging is going to get bigger. But if I push just random whenever I feel like it, I'm not going to help that much. There's a similar concept with sound called resonance. So resonance is when you match an object's natural frequency and it resounds that note, making it louder. That's called resonance, which literally means to resound. I am vibrating the rim of this large glass to match its natural frequency, which is a low note. This glass is a fair amount higher. And this one's even higher. We've already talked about how every object has a natural frequency. For air columns, that natural frequency depends on their length. The reason that this tube plays that note is because it has to have an antinode at both ends. So if you figure that the wavelength must be twice as long as the tube, take the speed of sound, which in air is usually 343 meters per second, divide by twice the tube length, and you'll get the natural frequency. These tubes are also able to support overtones when you vibrate them faster. So if I pick one of these boom whackers, it has one frequency that is its natural frequency. If I match that with a tuning fork, it will resonate. The sound is amplified. However, this tuning fork doesn't do anything for a different length tube. If I want to use a tube of this length, I need to have a lower frequency. Each frequency will only resonate tube lengths that match that natural frequency. These are open tubes, but I can also do this with a closed tube. If I have a closed tube that is being closed by water, I can make a variable tube length, kind of like how the trombone has a variable tube length. That allows me to find the right length to match the natural frequency of any tuning fork I pick. So this tuning fork is 288 hertz, so I can find the right tube length. But since this is a closed tube, the wavelength of the closed tube is 4 times the length from here to the water. Once I've found resonance, I simply multiply this distance by 4 to get the wavelength times by the frequency on the tuning fork, and I have the speed of sound. I can build up a loud vibration in this bar by putting rosin on my fingers and forming a longitudinal wave in the bar by pulling my hands across the bar. I grab the bar in the center so that I know my fingers are making a node right here in the middle. Then with each pull, I'm creating a longitudinal wave that I build up by adding to the reflected waves. A shorter bar will have a higher frequency. I can also resonate tubes by heating the air at the bottom of the tube. Here I have a long tube that wants to play a really low note. That note right there. And so all I need to do is match that note, get it to resonate, by vibrating the air by heating it. I have a little bit longer pipe. it's a little bit difficult to resonate because I can't stand it straight up. So I'll try to do it at an angle. All right, I want to talk to you a little bit about something called beat frequency and how it's used for tuning instruments. So beat frequency is the periodic reinforcement of a wave amplitude by another frequency that's just slightly off. So if I decided I want to go for a walk with my wife and I take 60 steps every minute and she takes 62 steps every minute, and we do it with a real regular cadence, there's a rule that we're going to step together twice. There's only 2 times during that minute that we're going to be stepping exactly together. When I'm taking my 30th step, she'll be taking her 31st. And when I'm taking my 60th step, she'll be taking her 62nd. So we step together twice. If I walk 60 steps in a minute and she walks 63, we're going to be stepping together 3 times. When I'm on 20, she'll be 21. When I'm on 40, she'll be 42. When I'm on 60, she'll be 63. There's a rule in math that all you have to do is subtract any 2 frequencies and you'll find out how often the 2 will be in phase. So if you take 400 hertz and 395 hertz, those are in phase 5 times per second. So you're going to hear a beat frequency that gives 5 beats per second. It will sound like whoa, 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 5 beats per second. If they were off by 2, it would sound more like whoa, 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 2 beats per second. So to get 2 notes together, you want to decrease the beat frequency until you don't hear that vibration at all. So I'm going to play 440 hertz on my computer over the classroom speakers. Fortunately, someone has put 2 hours of 440 hertz on YouTube. So now I will attempt to match that with another speaker, and I'll start with it slightly off. So I'm going to start at 435 hertz. I'll turn the volume up. And you should be able to hear 5 beats. Now, as I tune this, that beat frequency is going to slow down. That's only 1 beat there. Now we're in tune, we don't have a beat frequency. Now if I go above it, it'll start picking up again. Once you get to about 7 or 8 beats, it just starts to sound like dissonance, like a train sound. When I play a string, I can shorten it by holding down a fret. By holding the 5th fret of the low E string, it turns that into a higher note, an A, because the string is now only this long. That is the same note as the 2nd string. So I try to match those notes to tune the guitar to itself. But actually, when you pluck a string, it's supporting many vibrations at the same time. All of the overtones are also being heard. So to get a pure tone, you can make the harmonics ring out by just lightly touching the string. Those harmonics are different than the note you get if you actually fret it. So I use those harmonics for tuning. If I do the 5th fret of the E string as a harmonic, that's actually a node. The 7th fret is a node, and the 12th fret is a node. The 12th fret is the node that cuts the string in half, so it's with a node in the middle. That makes the 1st overtone ring out. That's at a quarter, so that's the 2nd. There's the 3rd. So I can use the 2nd overtone of the bottom string and the 3rd overtone of the 2nd string. Now if 2 strings are slightly off, you'll hear a beat frequency. Okay, if I tune 2 notes and I hear a whoa, 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 whoa sound, I know that they're slightly off. I tune to slow that beat frequency down. There, now I don't hear a beat frequency. And finally, a survey. You can let me know in the comments which one bothers you more, the sound of plastic sliding across the lab table or the sound of the steel bottom of the ring stand.